Welcome to today's Explainer. Today, we're exploring the absolute magic that happens when hard science meets digital art. We're going to uncover how the immutable laws of physics are secretly the true engine powering the most realistic, captivating digital animations we see today. You see, if you want your digital universes to feel real, you can't just draw them. You literally have to subject them to the exact same physical rules that govern our own universe. Okay, let's dive right into this. Here's our roadmap for today. We'll kick things off with the quest for realism, break down Newton's three laws, inertia, force and mass, and action and reaction, and then wrap up with a look at the future of simulation. All right, section 1, the quest for realism. So you gotta wonder, why does so many 3D animations end up feeling, well, floaty and robotic? I mean, we've all seen it, right? A character jumps, runs, or swings a sword, and it just feels completely off. They lack weight. They feel totally disconnected from their physical environment, moving way more like a camera panning through empty space than a creature made of flesh and bone. So, why exactly does this happen? Well, it often comes down to this overachiever syndrome, stemming from how animators are traditionally taught. If you strictly rely on the pose-to-pose technique, you're basically just defining keyframe A and keyframe B almost academically, but relying solely on that completely ignores the physical flow of a character. Realism isn't just about hitting the right poses, it's about the forces driving a character between those poses. To fix this, animators really have to focus primarily on the center of gravity, the pelvis and torso, to get perfectly credible timing and weight transfer long before they even start worrying about what the arms or legs are doing. Moving on to section 2. First law, mastering inertia. Okay, so the absolute foundation of our digital physics is the law of inertia. It basically states that an object is going to move with a constant velocity unless it's acted on by an unbalanced force. In a digital vacuum with zero gravity or friction, an object set in motion would just move in a perfectly straight line forever. But in reality, and in good animation for sure, forces are constantly acting upon objects. To really picture this, just imagine you're a passenger sitting in a moving car. You share the car's constant velocity. Now, when that car suddenly hits the brakes, the vehicle stops because of an unbalanced force. But hey, that force hasn't acted on you, the passenger, yet. Because of the law of inertia, your momentum continues forward until an unbalanced force, like a seatbelt, stops you. In animation, we call this follow-through. It's the exact same reason why clothing and hair drag behind a moving character. An object at rest stays at rest until it's actually forced to move. So, how in the world do we actually program that into software? Well, if we look at a kinematic timing curve, smooth inertia is represented by gently easing into and out of a motion naturally. But a physical object simply cannot stop instantly because of inertia. So animators use mathematical curves to simulate what we call anticipation at the start and overshoot at the end. That overshoot is literally the mathematical representation of a character flying slightly past their target and then settling back into place. And it gets cooler because animators can mathematically manipulate these kinematic curves using parameters like anticipation, midpoint, and bounces. By adjusting the bounces parameter, we simulate elastic restoring forces. Think of a character landing a really heavy jump. Their body compresses and slightly rebounds, oscillating kind of like a damped spring before finally coming to a rest. By applying these Newtonian equations, the software ensures the resulting animation is physically plausible, automatically giving us that vital sense of weight and follow-through. That brings us to section 3. Second law, force and mass. The famous equation, F equals ma, force equals mass times acceleration. This law tells us that an unbalanced force completely changes an object's momentum. And momentum is absolutely the magic word here. To convey force, whether that's gravity, friction, or a character throwing a massive punch, we have to understand that momentum depends heavily on both the speed and the weight of the object. Let's put this into perspective. Picture a lightweight bicycle and a massive, heavy truck. If that bike is moving incredibly fast, it might actually possess the exact same momentum as a slow-moving, heavy truck. Why does this matter for animation? Well, imagine both the bike and the truck hit a solid brick wall. Because momentum relies on weight and velocity, the wall has to exert a very specific amount of force to stop them. Showing this varying resistance to force is exactly how animators trick our brains into perceiving physical mass on a flat screen. And this is where weight transfer becomes absolutely crucial. Imagine a character trying to lift a super heavy bowling ball. They can't just stand perfectly straight. The action of pulling that heavy mass upwards and backwards creates momentum in that direction. So to avoid falling over, the character literally must step backwards to compensate for the sudden shift in their center of gravity. Plus, you have to signal weight through the relationship of effort and effect. High effort, like straining, leaning, shifting feet, combined with low effect, where the ball barely even moves, is what truly sells the illusion of immense mass.
All right, on to section 4. Third law, action and reaction.
This is the ultimate rule for interacting with an environment. For every action, there is an equal and opposite reaction. In a physics engine, this means forces don't just exist in a vacuum, they always exist in pairs. When a character pushes against a wall, the wall literally pushes back. Let's systematically build a simulation here using this law. Think about a rocket launch. It isn't just moving an object upwards. First, the engine generates upward thrust. That is the action. But it instantly meets opposing reactions. First, the inertia of the rocket's own mass. Second, the constant downward pull of gravity. And third, the atmospheric drag pushing against the hull as its velocity increases. By calculating all these opposing forces in real time, the simulation gives us a completely authentic dynamic launch, rather than just some static, boring upward glide.
And you actually see this exchange of forces everywhere, like a swimmer pushing off the wall of a pool. They exert force on the solid wall, and the wall pushes back with equal force, launching them forward through the water. The severity of that propulsion and exactly how the water reacts around them is how we visually measure the force of that initial impact. It's an incredible chain reaction.
Finally, section 5, the future of simulation.
You know, the days of painstakingly hand-drawing every single frame to fake these physics, they're completely evolving. We started out with ragdoll physics, where a character is basically treated as interconnected, rigid bodies reacting to gravity and impact. But tools like Cascader take it a massive step further. They can take a handcrafted artistic animation and mix it with physical simulation, automatically adjusting the character's poses to add that profound sense of weight and inertia we've been talking about. And now we even have AI systems using physics models to literally teach characters how to walk, grab, and move by simulating muscle contractions against a digital gravity.
So that leaves us with a pretty wild final question to think about. As AI and these advanced physics engines perfectly calculate Newton's laws down to the microsecond, how long is it going to take until our digital simulations become utterly indistinguishable from physical reality? I mean, we've gone from simply drawing pictures to mathematically simulating the fundamental rules of the universe itself. Thank you so much for joining me for this explainer, and definitely keep an eye out for those physical forces the next time you watch your favorite animated film.